Good morning, everyone. This is your TA Arthur speaking again. Today we're going to be going over the 2019 midterm twos. I couldn't find any of my 2018 midterms, so unfortunately this is all we have. So the very first question. This is the I believe here it goes. Spring 9. Is this spring? Yeah, this is the practice midterm that I wrote for midterm 2. Ignore the midterm 1. I forgot to erase that one and put a 2 there. This is for spring 2019. The first question was a subnet question, and it says a subnet of 192.168.4.0 is the first host and the last host is 192.168.4.255. Now the very first question is, what is the network address in a slash format? So if you didn't know, you already have the network IP address right here. And we know that this must be the network IP address because we have all zeros and the last octet or the last byte of the IP address. If you recall, if we have all zeros in the host, then we must assume that it is the reserved host for the network address. Now, why can we make this assumption? Well, we have a 4 here. This could potentially also be in the host ID, but as you notice, it states right here the last host is .4.255. So the third octet does not change in either of these IP addresses given. However, the last octet does, and it goes to the maximum value of the broadcast address. So we must we can assume that the network ID is therefore 192.168.4. And so that's why I have here 192.168.4.0. Now this slash 24 comes from the fact that I believe I explained this in my review video. We are looking at what changes between the first given IP address and the second given IP address. And then we can assign a given number of ones to bitwise AND these IP addresses to find out what is our host ID. And that will give us the subnet mask that we need to use. Now, I've done this often enough, and I know these tricks that I can immediately just see that it's slash 24. But if you don't know how, remember, you are almost always going to be working with just octets. There are potential subnet masks that do not fall within slash 8, slash 16, slash 24, but we likely will not give you one of those. And if we do, then it's going to be the same process that I'm going to describe. You just, well, I like starting from the left side and then working my way right. As you can tell, I described each one of these values between each dot as a octet because they are a byte each, and each byte contains 8 bits. So this will be 8, that's going to be 16, and that's going to be 24. And as you can see, the first 24 bits starting from the left side do not change, whereas the last 8 bits do change. So if we do 32 minus 8, we will get 24. Or you could just count 8 times 3, 8 plus 8 plus 8 is equal to 24. And so either way you work, you can come from the right hand side or you can come from the left hand side, whatever your understanding is to getting this value. Now, when you are actually doing CIDR addressing in the industry and whatnot, if you're working for Cisco, you will have to know the types of slash notations that you can get and the tricks associated with that. But this is not that kind of class, and you could look online for that if you so choose. Typically, we're just going to be working in the range of around slash 24. The highest subnet mask you will see will probably be a slash 16, but I doubt that I would give you a question like that on your exam. it's probably going to be something like slash 24, the highest being slash 22, and the lowest being slash 31. Okay, what is NAT and how does it work? You can read this right here. Just pause the video. And this is basically a good summarization of what NAT is. If you want to go into more detail, then you could look at my not review video. You can look at my video covering the IP slides. Okay. Question 3. Let's actually zoom in a bit here. Question 3. When a router receives an IP packet, draw its processing flowchart. You may use the backside of the paper instead of the given space. So here we have the packet being received, and then the very first action I believe that a router should do is check the destination IP address. So in the real world, where you have Cisco and a few other companies making these routers, obviously these routers are multifunctional for different protocols and doing different things, but this is just for an IP address checking, IP packet checking. And this is what I believe that a router should do. Now, we hammer a lot that TTL should be deducted by 1 whenever it goes hop by hop. And over here, I don't do that until I check if the IP address is not the same as the router. The reason I do this is because if TTL is currently equal to 1, right? And instead of after checking the IP address, I do it before. The logical step that occurs afterward must be checking if TTL is equal to 0 or greater to 0. Now again, I just said that the packet's TTL is equal to 1, and if we decrement it before checking the IP address, and if the packet belongs to you, you must drop that packet regardless. And this is because if we do it in the reverse way, right, and that if we just simply decrement the TTL and then the packet still doesn't belong to us, but it is greater, it is still 1, we wasted time processing and holding it when we could have just dropped it immediately. Whereas the reverse is also true. We decremented TTL when we didn't have to, and then even if we held it at 0 and then if it belongs to us, we just wasted a few milliseconds of time just checking if it belongs to us and then taking it straight away. So that's just an efficiency check right there. Really, it's up to the programmer, whoever makes the software that controls the network firmware on the network capable switch or router. But this is how I would write that software. And so if it belongs to the router, you check the flag bit to see if there's more fragments. If there are, you store and wait. If they're not, then we this should say send it to the appropriate transport layer protocol, not host application. This is a typo by me. And so if it doesn't belong, we decrement TTL. If it's equal to 0, drop it. If it's greater than 0, we check the routing table. And if the destination is in the routing table, no, then we go to default. Yes, then we check if the MTU. If it's greater than the MTU, then we have to fragment. If not, we send the packet. So, all in all, fairly straightforward, I believe. Oh, excuse me. And I hope everything made sense for you there. So, question 4 is about UDP. So, the very first part is how many bytes does a UDP header have? And really, if you remember how to answer part B, part A should be very simple to answer. There are only 4 fields in a UDP header, and each field is 2 bytes each. These 4 fields are the source and destination port number, the length, and the checksum. And so, since each are 2 bytes, then there must be 8 bytes in the UDP header. And I've already gone over part B, so in part C, what is the purpose of the UDP pseudo header? That's really just to calculate the checksum. I believe I've also talked about this in the review video, but for historical reasons, the IP addresses are still considered when calculating the checksum in the transport layer. and I think a few other fields. But that's just to ensure that the packet is correct. Technically, because it is UDP though, the calculation of a checksum is optional. So uh, take that as you will. Right here, this is not necessarily correct. It's not just to check if the destination has been reached, but it's also to check that to ensure that the integrity of the packet is there. Even though UDP packets are unreliable, that only refers to the transportation of the packet. Regardless of reliability or unreliability, all protocols ensure that the packet information maintains the same as when it was sent. Briefly describe UDP's flow and congestion control mechanism. So every semester there's at least one person that gets this kind of question wrong. Please, please, please do not get this question wrong. I feel so sad every time I see the wrong answer. UDP does not have any innate flow or congestion control. Remember that flow and congestion control in TCP is directly tied to the sequence and acknowledgement numbers, right? In flow control's case, there's also the receiving window size, and in congestion control's case, there is also RTT considerations, but all of that does not matter if the sequence and acknowledgement numbers do not line up. So, because UDP was designed to be unreliable, connectionless, and fast with the least amount of overhead as possible, it does not have any inherent flow and congestion control. It's not made to be that way. In the foreseeable future, it will not change to be that way. There are other protocols that can be used if you want those mechanisms. And so, please do not get this question wrong if I write it inside the exam. It makes me very sad, and I get slightly depressed grading your exams whenever I see at least one person have that. Alright, so in question 5, we have an MTU of 1500, and this is the first packet right here. It is a total length of 4000. We give you no ID, so you do not have to put that field inside the other fragments. So how do we split this up? Well, because the MTU is 1500 and we don't give any header information, you should assume that the header size is equal to 20 bytes. And so an MTU includes payload plus header. So that means that the payload that you can include in your fragment must be a maximum of only 1480. So I didn't have a calculator out, but let's just open that up so you can see. So 148, right? And so remember, we're doing bitwise shifts so that we can multiply it and divide by 8. So we divide this by 8 and we give 185. Now this is for the offset, remember that, right? So I already told you though that how to get this length here, 1500. So we set a more frag flag, and we set that to 1. The offset then is for bytes 0 to 184. And that still gives us the total offset of 185 bytes. But you must start at 0 here for the offset, because it is the very first fragment. So the second fragment is of equal length to the first, right? So if we actually do 4000 divided by 1500, we get that there should be approximately 2.6 packets, right? So we know that at the very least we will have 2 packets with a payload of 1500, or total length, not a payload, I apologize. So the payload for both then must be 1480. So what would the last one be? Well, all you have to do is just do a 4000 divided by the uh, 1480, let's see, times 2 there, and that gives us the final size, the final payload for the third fragment. And again, these are the same offsets because they are the same length. I mean, they are the same payload size. So this is going to be 0 to 185, and then this starts at 185 and goes all the way up to 369. And because it starts at 369, ends at 369, the offset on the last one must start at 370. And so from here, again, this is 140 plus 20 bytes of header, which gives us the total length here. And since this is the last fragment, we have a frag flag is equal to 0. And that's basically it for these kinds of questions. Now the more difficult thing is if we add additional pipelines to go through with smaller MTUs, in which case you just have to fragment it further. But it shouldn't be too hard. It's the same thing. Just remember to keep your math correct. Alrighty. And even though you shouldn't use, calculators in your exam, we're not going to tell you to record yourselves taking the exam. I believe if Frank asks you to do so, then please disregard my current statement, obviously. But unless he or I request that, which I won't be, then, if you need a calculator, whatever, am I going to dock points, or am I going to be able to tell? No, I write these questions so that they're easy to do by hand as well. So the only thing that I ask you to do is make sure that you aren't trying to look up these answers online. For the most part, most of these questions aren't going to have answers that are online, so don't waste your time, 1. And 2, really, you should just try to do these exams to the best of your abilities. And yeah, we don't try to fail you here. We try to give you every opportunity to at least pass the class. And the main thing we want you to come out of this class with is knowledge of networking. And I'll give you the truth, if you don't know, is that when you're working in the industry, your GPA is only important for your first job. And right now in the modern world, how the industry really works is you just need connections. There's a lot of company that are hiring fresh grads regardless of GPAs, or newer companies. But if you want to get into a established company, you need to have connections with it, or you need to be an extremely good talker. So sure, there are certain GPA requirements, but at the same time, there's a lot of advice that people give is also just, even if your GPA is low, go for it. And really, that's the truth there as well. I'm sorry, this is a review video for the midterm, but let's just turn this into a life lesson in that sense, that if they aren't doing automated filtering, then there's a good chance that if you put keywords in your resume, regardless of your GPA score, because you don't really have to put it in there, unless you're going through Handshake, they're not gonna know. I've never actually had an interview where they asked me what my GPA was. I just talked the talk, walked the walk, showed them I knew my stuff, and I've got picked up for both under the table jobs. I've been picked up for internships. I've been offered full-time positions just because I'm able to do the work that is requested of me. They don't care about my GPA. And I'll tell you right now, I did not have a perfect GPA. Obviously, I believe I ended somewhere close, if not a 3.5, but there are some classes that I just really struggled in with. But I still was able to land a 6-figure salary job, and that's because I knew what I was doing. And that's really what I want to hammer in this class is, please, if you want to actually excel outside of college, then you need to be able to, one, be sociable, and two, be able to ask questions if you need help, and then three, know the material without constantly looking it up. Obviously, when you're first starting out a job, if you do that, no one's gonna, hark you on it. Especially if you are doing internships as a college student or a fresh grad. But the moment that you are in your second job, they will be expecting you pretty much to ask minimal amount of questions. Um, but yeah, if you are going for that first time internship or you're still in college, take advantage of that. Most of the people actually that I've met in the industry are very kind towards students and will answer almost all of your questions whenever possible. All right, so enough of that ranting about how to get a job and what yada yada yada. Let's continue on to these review questions. Answer the following TCP questions. A. Briefly describe TCP flow control mechanism. Who's doing what to whom and how. Okay, so this is actually very important, so I'll go over these instead of just asking you to pause the video. Receiver maintains the sliding window, which is the amount of data it can currently process. Alright, so if you recall, there are transmitter and receiving buffers, right? And in these buffers, we have what is sometimes referred to as the sliding window, or also known as the receiving window for the receiver side. And the concept of the sliding window is that the receiver acknowledges the received packets, and once those packets are acknowledged and the client receives the acknowledgement, it will then drop the data from its buffer to put in new data. We'll buffer it in, and then it pushes out the data at the front of the buffer to the server. And at the same time, when the server finishes acknowledging the client's packets, then it will send those packets upwards to the application that requires it. So, as if you notice, if we do that process correctly, then it would be consistently sliding, so to speak. If you can, visualize that, what is occurring there, then there are animations out. Just look up TCP sliding window. But hopefully I said this, but I believe that if you just work with the sliding window idea, you lose a lot of understanding of how TCP is actually maintaining itself. If you believe that's 100% how the way it's done, there are other mechanisms that flow control has that we don't go over in this class, but the simplest one is just the sliding window, and the most commonly used one. So hopefully, if you didn't understand the explanation that has been shown there, and the way that I explained it in the review video, that you've looked it up already. But it's a relatively simple idea. The idea is, again, the client sends data and stores and maintains that data within its buffer until it receives the acknowledgement from the server. And once the server receives the acknowledgement back, plus the other data that's being sent to it, then it will send the data to the application that requires it. Obviously, this happens very fast, so the buffers should be maintaining a very nice sliding window of data coming in, data coming out. Okay. Briefly describe TCP's congestion control mechanism. Who detects what and does what? Oh yeah, I'm sorry. So who does what in the in part A is the receiver maintains the its window size and advertises it to the client, and the client just continues to pump out data as fast as possible until the advertised window is 0, in which case it just sends 1 byte of data until the sliding window, or rather the advertised receiving window, is greater than 1 byte. Alright, so in part B, the congestion control mechanism. So in flow control, the receiver is the one controlling everything, right? Now, the sender participates in flow control. Don't get me wrong, right? But participating and controlling are two different concepts here. The same thing within congestion control. In congestion control, the sender controls everything that is occurring because they are the one maintaining the RTT calculations. Now, could the server do this as well? Yes, because it's possible that the server is also sending data to the client, right? This is why we use the term sender and receiver. However, in respect to when receiving data, the receiver doesn't care about the round trip time of that. It should only care about the round trip time of their own data being sent, or rather their own packets. And the reason for this is because we do not want to congest the network. So the only way that the receiver can stop the sender from overloading the network is by having a complete overview of what packets are being sent from everybody in the network, which is quite literally impossible for the most part, right? Unless we're using some sort of highly advanced centralized system. But what it can do is it can ensure that it can make the only thing it can do, since it can't control everyone else, is control its own packets. And if its own packets are going outside of its RTT time, then it will slow itself down. So this is why the sender, right, is the one that controls it, because the receiver is just receiving packets. It can, stop gate the sender by saying, hey, I don't have any more space. But the moment that it starts sending packets out for, its own purposes, it becomes a sender. So in that case, it has to ensure and maintain a RTT where nothing is lost or dropped or has any, loss events. But if there are, it should handle that accordingly to make sure that the network is not congested. So again, long story short, only the sender controls congestion control. And it does so by checking for any loss events. Whereas in TCP flow control, you have the receiver that controls the flow through the receiving window or sliding window, whatever you want to call it. Receiving window is a better technical term and would be the one I suggest you use. Sliding window is more referring to the action that's occurring. So please try to use receiving window instead of sliding window. See how many bytes can a TCP header have, minimum, maximum. TCP header, as well as the IP header, has a minimum of 20 bytes and a maximum of 60 bytes. Why is TCP reliable? TCP attempts to recover lost packets based on the sequence and acknowledgement numbers, and that is why it's reliable. Reliability, again, I pretty much explained that as well up here in UDP, is really in part because of the sequence and acknowledgement numbers. And I already went on a rant earlier, wasting some time about jobs and stuff, so I'm just gonna continue. Complete the 7. Complete the following ladder diagram between TCP client and server with minimum additional packets for disconnect. Three-way handshake has not been established. Add whatever is missing and delete whatever is extra. Alright, so when I gave this, there was already pre-written stuff in here, but this is again the answers to the exams, so you get to see everything. So since three-way handshake was not yet established, and we do not give you an ISN, initial sequence number, sequence is 0, bytes is 0, and acknowledgement is 0. Now bytes is the payload, so this could be length as well. The professor put length in the very first exam that I took, or at the second midterm exam, so sometimes I switch between bytes and length, but they're the same thing. It's just the payload. It's how much data is one side sending the other. And then sequence and acknowledgements are obviously the same thing. But recall, hopefully if I explained this, I don't recall if I explained when you have a singular SYN, the very first one, right, will always be singular, and there is no payload, we must increase it by 1. And this is what I'm talking about here. This is the three-way handshake. If we do not acknowledge 1, right, if the server does not do that, then the client, right, is going to have a sequence of 0 here. And because of the SYN again, ACK is its own separate thing. A SYN ACK is still just really a SYN. Again, after this first packet right here, every subsequent packet has an ACK flag set. So really this is just a SYN packet as well. Or rather it's a combination of a SYN plus the additional ACK packet from the original 4-way handshake to make the 3-way handshake, if you recall that in class. And so we also need to increment it by 1. And notice if you do not do these increments, right, this would be acknowledging 0. And so if we have sequence of 0 here, byte 0, acknowledge is equal to 0, what does that match up? Well, this matches up with exactly the very first packet. So then you acknowledge then sequence is equal to 0, bytes is equal to 0, ACK is equal to 0. And the server is going to say, well, what the hell are you on about? You know, if sequence is 0, alright, so then we go back here. So, okay, since you're acknowledging something, then I will acknowledge something back, or I will do a SYN acknowledge back. And so you'll be stuck in an infinite loop somewhere within this handshake. Typically, you won't even get to the third ACK. The client will just assume, hey, since you're saying sequence, you're acknowledging 0, and I already sent sequence 0, I will attempt to resend it, which is this packet right here. But it is possible, again, that you handle that case within your netcode, or rather your TCP protocol code, to just send the acknowledgement. But the server might not have it set up in such a way, so you get stuck in a loop here. But yeah, pretty much whenever you use SYN and FIN by itself, you know, disregarding ACKs, you must increment the acknowledgements by 1, so that the subsequent sequence number is increased by 1 to prevent an infinite loop. Usually you will see a part up here that says packet type. Really everything after the 3-way handshake and then everything before the closings are just, pardon me, typical data transfer packets. They don't really have a type, and we aren't really looking for that. Really, we're just looking for the SYN, SYN-ACK, ACK, and then FIN-ACK, FIN-ACK, or FIN-ACK, ACK, or FIN-FIN-ACK type of stuff up there. Everything else, you could keep ACK on top because why not? You're not wrong, but it's probably going to be less clutter if you just leave it empty, as shown right here. So, finally, we can continue on to the actual data transfers. So, acknowledging 100 here, that's just blatantly wrong. How can you acknowledge 100? As you can tell from the finishing of the 3-way handshake, you should be acknowledging a sequence of 1, or you should be expecting that, and there's a payload of 10 here. So the way you get the acknowledgement value again is you just add the sequence number value plus the payload value, and that should be your acknowledgement value. And then you're acknowledging 1 here, so your sequence should be a 1 here as well. That's how you just make sure that there's logical consistencies within your transfers. And then we're sending from the server side a payload of 20. So adding these together, we have a 21. Yep, right there. And then we're acknowledging 11, so we're starting at sequence 11. Yep, that makes sense. And we already checked here, so that should be right. And so everything should be right here. And we have a payload of 30. 30 plus 11, that's 41. Yep. Acknowledgement of 21. Yep. And there's a bytes of 0 there. Now, you should arguably, right here, either include a acknowledgement right here, not a fin, or a fin ack here. Now this is in hindsight, right? I should not have a fin by itself here. This should either be an acknowledgement first and then a fin below it, or a fin ack. This is because the server is acknowledging something, even though it's sending nothing. But we should be, again, every subsequent packet below this SYN should pretty much just have an acknowledgement there. But in this case, because nothing is being sent and there's no values being changed, technically, you know, it is possible that you could just send a fin right here. But I would suggest you get into the habit of not sending just a fin by itself. Mostly because if you do this, then you have either a four-way like this, or you have to do a fin ack. It's cleaner to just do the fin ack. But this should be pretty self-explanatory as well. So we have a fin here though, and so you have a 41 here. There's no bytes being sent obviously because we're trying to close the connection, but it is possible to send data still, just for you to know. And we're acknowledging 21 right there as expected, acknowledging 41. And again over here, because this is a fin by itself, we have to increase the acknowledgement value, and sequence is 21. So immediately after, we are sending our own fin and still acknowledging 42. I said 41 here, I meant 42. At the top of my head, I don't remember if this is actually right. This might have to be a yeah, this is wrong. This should be a 41 here. This should be the 42. Disregard this 42 here. This should be a 41, and this should be 42. So this is right. This acknowledgement is wrong. This should be 21 0 41. But this is correct, 21 0 42. And then the final acknowledgement though is correct. You are at 42 0 with an acknowledgement of 22, even if though this is the end. Okay, so that's that. Oh man, this is getting a bit longer than I expected. Maybe I'll cut up these videos, so each video for one. That'd probably be better. All right, so this is this is the link state algorithm. This should not say shortest path. This should say link state. But here I just have just three nodes for the same one, and we just have a y, x, and z. This is actually, I think, almost the same, or the exact same as the on the slides. But as you can see, for node x, so we start at x. Step 0, we check the shortest path for each connection we have. So from x to z, as seen over here, we have a cost of 2, as seen right here. And then from x to y, as seen right there, we have a cost of 7, as seen right there. Clearly, we should take the path of 2. So that's why we have a xz here. There should be a step 2 here, actually. But now our next step is, okay, now we have access to z, and we can send stuff from x to z to something else. Now, what is the path? Well, x to y, directly hasn't changed, but when we include z, we have a cost of 3. So over here, the shortest path would be from x to z. We can send a packet to y with a cost of 3. So that's why we have a z here, because this is the node before y that is the incoming packet is coming from, and the cost associated with it is 3. Right. So what are the routing? What this should say? What is the routing table for node Y? And this is what is the routing table. I did not show the routing table in here for both of them actually. So that is an issue in itself. But if I were to do a routing table, let's just open a notepad. Right. So what I would be expecting in a routing table, let's go with a font of size 20. Yeah, that's clear enough. So basically what I'm looking for in a routing table would be something like from X, and then you could just do like from X like that, and then to Z, and then to you can just do X like that, to Y, and then I'm trying to make a table here, sorry guys. And then cost, obviously, let's try to match that up. And then the cost to Z, what did we have here? We had a 2, and then that's from X, right? And then a cost to Y, and that should be 3 from Z there. And that's basically the routing table. Really, a real routing table will have interfaces, and you would show the interfaces and that you would use and the cost associated with those interfaces. But in here, this table, this topography is very simple. So for the midterm, I think I'm gonna give you interfaces. But yeah, so if it had interfaces, right, I would say like Y has a IP address. Let's just do 192.102.4.0/24, and then Z would, let's just do almost the same thing, but then let's do a 64 there, and let's change this to a 32. Right. And so instead of 2Y to Z, you would just have interface here, and then the cost like that. Interface. So if we want to send it to Y, right, which is this interface right here, interface. So let's just put, yeah, let's put this like that. And then the associated cost, which was again from Y, which was from 3. And then let's expand that a bit there. Cost slash from. And we are going to use here. Right. Okay, and so since we know this is from X, you could just do it like this as well. And then the interface that we want to reach next now is Z there. This should be a /24, sorry. And then the cost is going to be a 2, as seen there. And then we are going to go from, oh, I didn't even give an interface for X. So the interface for X, let's just say it's this. And let's just say it's 17. Oops, what are those? And this is actually what a typical routing table or forwarding table pretty much will look like, something similar to this, where you have the interfaces and the associated cost, and then where is it coming from? The interface you want to send to, the associated cost. This you might not see sometimes. You just have the interface and the cost to reach the interface. But this would be an actual routing table, something like this. As you can see here, this is not a routing table. In here, this is just a shorthand notation of just getting the shortest path for the cost associated with it. But a routing table would be something that I had shown just like that. And again, for the actual exam, I will be now giving you interfaces for you to send to. So please make your routing table look like this, and do not think that this is your routing table. This is, disregard what I have here. This is incorrect. This is just to get the shortest path. This is not a routing table. And then distance vector, or in this case, distributed Bellman-Ford for node Y. Now, I do not create the routing table for node Y, but let's again just go over this real quick. Okay, so again, when you're doing a distance vector algorithm, I want you all to make the table for each individual node first. Okay, and so here we have node table X, or node for table X. This is such a real. Why did I word it this way? This is the table for node X. Why is it node table X? What the? Okay, so from X to itself is 0, obviously. To Y from X is 7, and then to Z from X is 2. Likewise, you'll see infinity just stands for unreachable in this case. And everything else is still the same. So from Y, 0 to itself. From X, it's still 7. And then to Z is 1, as seen there. And everything, the same thing for Z. And you could just scroll back up and see they're all still the same. And so there are 3 individual tables, and then there would be, I believe there's 8 iterations, I don't remember, that you have to go through to get this final routing table. Do note that, this is not a routing table, I'm sorry. To get the total cost table. Actually, I mean, again, this could be a routing table per se because we don't give you the interfaces, but in your exam you will be given interfaces. So here we have, please note that because it is symmetrical right here on both sides. I'm talking for too long again. I'm sorry, everyone. But again, so from X to X is 0, from Y to Y itself is 0, from Z to Z is 0, and then again from X to Y it's the same as before, the same table, so it's obviously going to be 3, and then to Z is 2. And since this is true for this topography right here, and because you must assume that each cost going from each node is the same for all of them. Going from X to Z is the same as going from Z to X in this image. We will have a symmetrical graph here. Now, if on the other hand I give you a graph where I tell you, or if I give you delays like from X to Z is 2, but from Z to X is 3, right? You would have to adjust accordingly. But because I don't write that in there, you could just assume that going back and forth between X and Z, nothing is explained in the question that's given. You should assume that it is the same cost going to and fro from every node. Alright, so that is it for the midterm 2 practice exam for, this should say, yeah, this should say 2 here, but this is spring 19 practice exam 2. And in the next video, I'll go over, what is it, the actual exam, which is right here. So I'm going to cut this one and start the next one.